In this video, we are going to discuss about built-in self technique. So, in this technique, the part of the circuit is used as a test circuit for itself. So, we can classify the BIST according to the based on the logic block and memory. Okay. So, the logic can be classified into online and offline. For online, we have a concurrent and non-current technique, and for offline also, we have a functional and structural technique. The same classification is applicable for the memory also. So, what is online BIST means, which is used to perform the test under the normal condition, whereas offline BIST means it is used to perform the test offline. So the advantages of the BIST technique is it is used to detect the delay faults, single structured faults, and it can able to test many units in parallel. It will reduce storage and maintenance of the test pattern, and for generation of the test vector, it will require low cost. So let us discuss about the circuit module required for the BIST. It consists of pseudo random pattern generator PRPG, which is used to produce the input signal for the circuit under test, whereas the output response analyzer ORA that is used to observe the output signal. So both uses LFSR, that is linear feedback shift registers. First, let us discuss about PRPG. It is also called as a weighted test generator or automated test generator. So, why it is called as pseudo random means it is not truly a random signal. It can also act as a parallel PRPG if I take the output from these three flip-flops. Okay, so the initial state of the Q0, Q1 and Q2 should not be 0. Okay, so let us discuss. You can see here I can term this one as if this is my H0, H1, and H2. That is, I have three flip flops, so the n values here is 3. Okay, so um, so here it is. This is H0, H1, H2, and H3. Okay, here H3 value is 1, H1 value is 1, and H0 value is also 1. So it is it's more or like a shift registers, and you have a XOR gate. Okay, so we have to find the characteristic polynomial f of x that is equal to summation I is equal to 0 to n, and here n is number of flip flops, or it is also called as the LFSR degree, or this fx is also or it is also called as characteristic polynomial degree. Okay, since I of 0 is equal to 3, I of 0 is equal to 0 to 3, and hi xi, this is the formula, and if I substitute, I will get h0 x0 plus h1 into x plus h2 into x square plus h3 into x cube. So here the h0, h1 and h3 is 1. So if I substitute, I will get the characteristics equation as 1 plus x3. Okay, so let me take the initial state, that is the seed value as 100, and you know what it is doing. So here the q, if you see this on this diagram, so what is q2 plus sorry, q0, q1, q2, q2 plus value is equal to q1 xr q0, right? So you substitute here. So initial value of the seed signal is 100. Okay, and I am going to give Q2. I'm going to write what is Q2. Q2 plus is equal to Q1 XR Q0. If I XR Q1 with Q0, I will get um, 0 is 0. Okay, and these two value get shifted. Okay, again you see 0 is sorry, 0 1 is XR with 0 1, you will get 1. Okay, and these two value get shifted. So 0 XR 1 is 1, and these two value get shifted, and 1 XR 0 is 1, so 1 1, and 1 XR 1 is 0 and 1 1, and here also 1 XR 1 is 0 and 0 1 you will get, and 0 XR 1 is 1 and you will get 0 0. Okay, so these values get repeated. So if you see there are 0 to 6 states, so I can write the periodical value L is equal to 7. So since the value of n is 3, so it is equal to 2 power n minus 1. So these combination it may not be cover all the 2 power n input combinations. Okay, so if it covers all the sequence, that is 0 to 7, okay, then it is called as a maximum length sequence. Okay, it is called as M sequence. But here since there is no long sequence, the fault coverage will be poor. So let us discuss about the procedure or block diagram for the BIST. So it consists of the circuit under test, and you have a PRPG block and ORA block. So the test controller will control the my PRPG block, mux, circuit under test, ORA, ROM, etc. ROM. Okay, so here the mux will select the either the normal output will be given to a circuit, or it will select the PRPG output. Okay, so the output of the circuit is connected to a ORA block, output response analyzer, and that will generate a signature. Okay, so that will be compared with my reference signature that is stored in the my RAM. So if the both the values are matching, means I will get the good output. Okay, that is, it is passed. So if the reference signature and my signature is differs, means it is a faulty output. Okay, so let us discuss the disadvantage of the BIST technique. The chip area get increased due to the test controller, PRPG block and ORA block. That are the extra blocks we are adding. But you know the time get reduced, right? So due to the increase in the area, reliability get decreased, and there will be a yield loss, and there is also increase in the complexities. So this BIST cannot be able to test the wires. So in the linear feedback shift registers, you know that the initial state may not be 0, but this condition is required in some situations. Therefore, in addition to the XOR gate, I have added one NOR gate, and this is my connection. Because due to this connection, the initial state will go to 0 0. Okay. So the next topic is signature analysis. Okay. So this is a circuit that is given. Okay, it is nothing but a D flip flop. So in the D flip flop, you see the clock is get connected. So So it is nothing but shift registers. Is nothing but a linear feedback shift register. In addition to that, you have a input bit stream. Okay, so here what I am going to do is I am going to find the characteristics polynomial from this block diagram. So you know that you have 5 flip-flops. So p of x is equal to summation 0 to 5 hi xi. Okay, and this is starting from h0, h1, h2, h2, h3, and h4 and h5. So here the h3, h2 and h4 is equal to 0. So you substitute in this equation, you will get 1 plus x3 plus x5. Okay, suppose this is the input bit stream that we are going to give, that is 0 1 0 1 0001. So this I can write it as for 1 it is 0. So I'm omitting this one. So this is x and this is x square. So this also I'm omitting. This is x cube, x4, x5, x6, x7. So I have x, x3 and x7. So this is my input polynomial. So this input polynomial I'm going to divide. So this is my input polynomial. So if I input the if I in order to get the remainder, I'm going to divide the input polynomial by the characteristics polynomial. Okay. So what is primitive polynomial? So the primitive polynomial is nothing but it is of the maximum length sequence. That is from 1 to x5. If I am getting, that is called as primitive polynomial. So it is nothing but irreducible polynomial. Okay. So I am going to generate a signature for my input stream. How can it be done means, so since I have 5 flip-flops, I am going to write 0 x q0 to q0 and the initial state is uh, 5 zeros. Okay. From the diagram, I can write q0 plus is equal to q4 XR with initial state, right? You can see what is q0 plus. The q0 plus is equal to um, uh, this is from q4, right? So q4 XR with input bit stream. Okay. So this is my input bit stream, right? So what is my input bit stream? One input bit stream, I'm going to write it as um, 0 1 0 1 triple 0 1. So this I am going to write it as 1 triple 0 1 0 1 1 0. Okay, 1 triple 0 1 0 1 0. Okay, so I am going to find q naught plus is equal to q4 XR my initial state, and q1 plus is equal to q naught XR q4. You see the diagram, q1 plus is equal to q naught XR q4. Similar way, I can write q3 plus. q3 plus is equal to q2 XR q4. So the rest of the values, that is q2 and q4, I can find it from this. If I shift the values of q1, I will get the q2 plus value and q4 plus value. Okay. So if I substitute, I will get the answer like this. Okay. So you can see. So if I substitute, I will get the answer as 10110. Okay. So I can write the remainder polynomial. That is this one. Okay. 1011. Okay. So this I can write it as 1 plus x2 because x is 0. So 1 plus x2 plus x3. So this is my remainder polynomial. So you can see the remainder polynomial is always less than the p of x. Okay. So I can write the f of x that is equal to q of x into p of x plus r of x, where q of x is nothing but my output sequence. So in the signature analysis, it uses the polynomial division. which divides the polynomial representation of the test output data by a characteristics polynomial p of x, and then it finds a remainder, that is nothing but a signature. Okay, so this signature is compared with the expected signature in order to detect whether the device under test is faulty or not. Okay, so the fault can go undetected in the signature analysis due to the compression technique. That is, it will reduces the fault coverage. So such phenomenon is called as aliasing. So in this example, we have taken the input bit stream as 0 1 0 1 triple 0 1, which we have compressed into a Unicode. That is the signature we have generated. That is as 1011. So using the data compression technique, it is called as a signature. So here the signature analysis uses the cycle redundance technique, right? So here I am going to give the this is my signature, right? So this is my signature value, that is nothing but 111101, right? This is my signature. So I'm going to the initial state is 00000, and if I substitute, we already know the formula, right? What is q naught plus and q1 plus and q4 plus, right? So this is my formula. So q3 plus, right? q4 plus is nothing but q3, and q2 plus is nothing but q1. Okay, so if you substitute this in this formula, I will get the this value 1 4 zeros and double 1 triple 0 and 0 11 00 and 10110. So if you see, at last I will get the remainder as 1011. So if this is the case, I can tell it is a faultless output, because the signature and the reference signature get uh, is same, so there is no error in this mode. So next, let us discuss about built-in logic block observation. So here this technique you will use both LFSR technique and also the signature analysis. So if you see, you can have the LFSR block also, and also you have a signature analysis. Okay, so it will operate in 4 modes. So whenever the C1 and the C0 value is 00, it is in the scan mode, and 01, it is in the test mode. That is, it can act as a uh, PRPG, or that it also acts as a signature analyzer, and 10 it is act as a reset, and for 11 it will act as a normal mode. So if I give 10, so if I give 0, it will be in the reset mode. Okay, so this is my first case. If I give 10, you can see this will be 0. Okay, this will be 0, and whatever the value that I am giving from the, so for 0 the SI value gets selected. Okay, so if it is 1, then this is also 0, so this will go to 0, so my output also goes to 0, and you can see this value is 1, so the input value also goes to 0 0. So you can see here since it is 1 0, this will go to all the values will go to 0. The flip-flops value goes to initial state as 0. Okay. So whenever if I select the selection pin as 0 0. Okay. If I select the selection pin as 0 0, okay, here the SI get selected, right? So the SI get selected, so this becomes now this becomes SI bar, right? And here since this value is 0, I will get here SI bar. Okay, so the SI bar will be stored in the output of the this one. So whenever if I give 0 0, there is a inversion between the each stage. So the flip flops will be configured as a 3-bit shift register between a SA and S naught, and there is a inversion between the each stage. So whenever if I select the test mode, that is 0 and 1, okay, the resistance will be behave as a PR SG or signature analysis. If the D input is held low, the Q output loop through the pseudo random bit sequence, which can serve as a input to the combination logic. So if the D inputs are taken from the combinational logic input, they are result with the existing state to produce a syndrome. Okay. So that is if the D value, if it is not taken, means it will act as a PRPG, PRSG, or it will be if it is if I am taking the values from D input, means it will be act as a signature analysis. So so next, and you can see since both registers are placed in the test mode, in order to produce this pseudo random inputs and calculate the syndrome, finally the syndrome is shifted out to the scan chain. Okay, so first what it will do, first it will reset the flip flop, then it will go to the test mode, then it will go to the scan mode. Okay, so if I want to perform the normal operation, I will have to select it as 1 1. Okay, so this is my a block. It consists of both the PRSG and signature analyzer. Okay, so here the PRPG and sorry, this built-in logical block observer is placed between the circuit under the test. So if you want to get the SI serial input and scan input and scan output, you can use it like this. So it will cover 99.7% of fault coverage level. So this kind of test method is incredibly valuable for productivity in manufacturing test generation. So if I want to check the memory BIST, means on many chips the memory account for the majority of the transistors. So a robot testing methodology must be applied to provide the reliable parts. So in a typical M-BIST schemes, multiplexers are placed on the address and data and control inputs for the memory to allow the direct access during the test. So during the testing, a state machine use this multiplexer to directly write checkboard patterns of alternating ones and zeros, and the data is read back, checked, then reverse pattern is also applied and checked. So this ROM testing is even more simpler, and the contents are read out to a signature analysis in order to produce the syndrome.